Welcome to Statistics, where we bring complexity to clarity. I am excited to have you join me for our 21st unit RBD, that is Randomized Block Design. Let's begin our journey of Randomized Block Design, that is RBD. In common parlance, Randomized Complete Block Design RCBD is spoken as Randomized Block Design RBD. The word complete is implicit. If the experimental units show one-way variation, the effect of this kind of heterogeneity is taken care of by grouping the experimental units into blocks in such a way that the units are homogeneous within a block, but there is every possibility of heterogeneity among blocks. Each block consists of as many experimental units as the number of treatments. The treatments are allocated randomly to the experimental units within each block independently such that each replicated as many times as the number of blocks or the number of replications for the treatments. In this design, all the treatments are equi-replicated. Sometimes blocks are also termed as replications. Randomized block designs are used in field experiments where the soil fertility is varying in one direction. Here you can see that the soil fertility is varying in horizontal direction. Blocks are always formed in a direction perpendicular to fertility gradient. So here the blocks are arranged vertically, that is perpendicular to the fertility gradient. Randomized block design is one restrictional design. Let's see the layout plan for randomized block design. Here we have 4 treatments, namely A, B, C and D, and 3 replications. Thus, there will be 3 cross 4, that is 12 number of plots. In the first case, here we can see that fertility gradient is in horizontal direction. Hence, the blocks are arranged in vertical direction, that is perpendicular to the fertility gradient. And within the block, the treatments are randomly allocated. Also, the treatments cannot be repeated in the direction of fertility gradient. That is, if treatment A is allocated here, at these places we cannot allocate treatment A. Now, in the second case, the fertility gradient is in vertical direction and hence the blocks are arranged in horizontal direction, that is perpendicular to the fertility gradient. And within the blocks, the treatments are arranged randomly. Here also, suppose we have assigned treatment A here, then at these places we cannot allot treatment A. Hence, RBD depends on the fertility gradient and so it is one restrictional design. Let's see the statistical model of RBD. It is Yij is equal to mu plus tau I plus beta j plus epsilon ij, where Yij is equal to response of yield from jth unit receiving the ith treatment, mu is equal to true mean effect or general mean, tau I is equal to true effect of ith treatment, beta j is equal to effect of jth replication, epsilon ij is equal to uncontrolled variation associated with jth unit receiving ith treatment. Now, let's discuss the procedure for analysis of RBD in stepwise manner. The first step is calculation of correction factor, that is CF, which is equal to grand total square divided by R into T, where R is equal to number of replication of treatments and T is equal to number of treatments. Step 2 is calculation of general mean, that is GM, which is equal to grand total divided by R into T. Step 3 is calculation of total SS, which is equal to double summation I is equal to 1 up to T, J is equal to 1 up to R, Yij square minus CF. For our example, we can write it as Y11 square plus Y12 square plus Y13 square plus up till plus Y34 square minus CF. Because in our example, we have 4 treatments and 3 replications. hence up till y34 square. Fourth step is calculation of replication SS, which is equal to summation j is equal to 1 up to ry dot j square divided by t minus cf, which is equal to y dot 1 square plus y dot 2 square plus y dot 3 square divided by 4 minus cf. Because we have 3 replications and 4 treatments. Step 5 is calculation of treatment SS, which is equal to summation I is equal to 1 up to t yi dot square divided by r minus cf. For our example, we can write it as y1 dot square plus y2 dot square plus y3 dot square plus y4 dot square divided by 3 minus cf, because we have 3 replications and 4 treatments. Here, in the formula for replication and treatment SS, the denominator in case of replication SS is number of treatment, that is T, and in case of treatment SS, it is number of replications, that is R. Step 6 is calculation of error SS, which is equal to total SS minus treatment SS minus replication SS. Step 7 is calculation of replication mean square, that is MSR, which is equal to the ratio of replication SS to replication degree of freedom. Step 8 is calculation of treatment mean square, that is MST, which is equal to ratio of treatment SS to treatment degree of freedom. Step 9 is calculation of error mean square, that is MSE, which is the ratio of error SS to error degree of freedom. Step 10 is calculation of F. So calculated F for replication is ratio of MS replication to MS of error. And for treatment, calculated F is equal to ratio of MS of treatment to the MS of error. Now let's see step 11, that is prepare ANOVA for randomized block design. The ANOVA constitutes of source of variation, which includes replication, treatment, error, and total. The degree of freedom for replication is r-1, for treatment t-1, for error t-1 into r-1, and for total rt-1. Sum of squares SS can be calculated using the formula which we have discussed in the previous steps. Similarly, MS and calculated F can also be computed using the formula we discussed, or the formula which is given in the table. For SS, this term indicates correction factor. Now let's see the interpretation. If calculated F is less than table F at 5% level of significance and treatment DF, error DF, the observed difference is non-significant and hence H0 is accepted, that is, all treatment means are equal. And if calculated F is greater than equal to table F at 5% level of significance and treatment DF, error DF, then observed difference is significant. Hence, H0 is rejected, which means at least one pair of treatment means are significantly different. Step 12 is calculation of SEM, that is standard error of mean. SEM is equal to root MSE divided by R. Step 13 is if F is significant. So here in this case, if F is non-significant, we do not need to calculate LSD or CD. But if F is significant, then we calculate LSD or CD using the formula statistic T at 5% level of significance and error degree of freedom into root 2 into SEM. Step 14 is calculation of coefficient of variation, that is CV% is equal to root MSE divided by GM into 100, where GM is the general mean. Now let's see the advantages of RBD. Blocking reduces the sum of squares due to experimental error, so it increases the efficiency of design as compared to CRD. The design is feasible with any number of treatments and block subjects to the basic requirements of the design. For instance, there should be at least 2 blocks to provide an estimate of error variance and a test of significance. The number of replicates should be enough to contribute at least 12 degrees of freedom to error. Control treatments can easily be included without causing any complications in the analysis of data. The statistical analysis is simple and less time consuming. The problem of 1 or 2 missing observations can easily be tackled. The error mean square for RBD is 60% to that of CRD error mean square. CRD required 10 replicates to get the same amount of information as we get from 6 replicates of RBD, which we can infer from the previous point. Let's see the disadvantages of RBD. It cannot accommodate a large number of treatments since in this situation the homogeneity of groups or blocks is always in jeopardy. In many situations, the criteria for blocking or grouping is not easily selectable. Usually, the blocks are not as homogeneous as are taken to be. Thank you for joining me on this journey through our 21st unit, RBD, that is Randomized Block Design. If you found this unit helpful, don't forget to like, share and subscribe to StatIsDates for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.